The universe is quiet now. Not the soft silence you hear when you step outside on a calm night, but a deeper stillness, an absence of the familiar cosmic heartbeat that once pulsed through every corner of space. Imagine drifting there, weightless, as if time itself has thinned to something almost transparent. The nearest star is impossibly far away, a lonely ember glowing with the faintest red light, stretched and weakened by trillions of years of expansion. Around you, the darkness is different from the darkness we know, colder, emptier, stretched across distances that make even today's intergalactic gaps feel intimate. This is a far future universe, not millions or billions of years ahead, but numbers so large they strain language. Quadrillions, quintillions, timescales so enormous that human history, every birth, every civilization, every star humanity ever saw, compresses into a thin, negligible slice of cosmic memory. Here, the temperature has fallen toward nearly absolute zero. The cosmic microwave background, once a bright flash of radiation released 380,000 years after the Big Bang, has faded into wavelengths so long they're larger than galaxies. There is no blue sky, no galaxies in the distance, no clusters, no filaments, just a vast, slowly cooling emptiness where the structures of the universe have dissolved into isolation. And yet in this stillness, something strange and profound lingers. The question of whether time itself can continue in a universe that no longer changes. What you're seeing in this imagined vantage point at the end of all cosmic evolution is not fantasy. It's the logical extension of what modern cosmology predicts. Physics allows us to peer into eras so distant that they make even the lifetime of stars look brief. Scientists like Freeman Dyson, Stephen Hawking, Roger Penrose, Lawrence Krauss, and many others have mapped out theoretical futures of the cosmos that stretch far beyond the comfort zone of human intuition. The numbers are extraordinary, but they're grounded in equations we use every day to understand stars, galaxies, and the expanding universe. As you float in this imagined end-of-time landscape, the question becomes far more than scientific curiosity. It becomes philosophical. What is time when there is nothing left to measure it by? Time, as understood in physics, isn't just a ticking clock. It's change, motion, entropy, processes unfolding from one state into another. If the universe eventually reaches a condition where nothing changes, no stars burning, no particles interacting, no radiation bouncing from one thing to another, does time continue, or does it simply lose meaning? This moment, this silent cosmic field, is where the episode begins. Before we go deeper, if you enjoy exploring these vast, quiet corners of the cosmos, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow, and it keeps these journeys alive. As your imagination settles into this distant era, look around. The universe was once vibrant, full of stellar nurseries glowing with the blue light of newborn suns, galaxies colliding in grand cosmic dances, and planets orbiting their stars like quiet companions. But long after the last star has flickered and collapsed, that era has ended. The night sky is nearly empty. The expansion of space has stretched matter so thin that most regions now contain almost nothing at all, maybe a few particles drifting through cubic light-years of vacuum. It's not just that stars have burned through their fuel. That's only the beginning. What happens is a slow cascading of cosmic structures unraveling. Over unimaginable durations, galaxies lose stars through gravitational encounters. The universe, which once formed dense webs of matter, gradually becomes diffuse. The last red dwarfs, tiny stars with lifespans measured in trillions of years, finally fade into black dwarfs, frozen remnants barely distinguishable from the cold around them. White dwarfs cool, neutron stars drift in silence, and black holes grow in relative dominance as other forms of structure decay. Even black holes, which feel, in today's universe, like the ultimate final stage, are temporary on sufficiently long timelines. As Stephen Hawking famously showed, they evaporate, slowly for small ones, absurdly slowly for the massive ones that anchor galaxies today. But evaporation is relentless, and in the far future of the cosmos, even they will be gone. What's left after the last black hole evaporates isn't a blank nothingness, but an incredibly sparse sea of particles, occasionally interacting through forces so weak and infrequent that the notion of events becomes almost meaningless. Entropy, nature's tendency to spread energy out, continues creeping toward its maximal value. When everything is dispersed, when no concentrated pockets of usable energy remain, the universe reaches what's known as heat death. Heat death is not dramatic, it's not an explosion or a collapse, it's a quiet settling, a fading, a universe that simply runs out of ways to do anything new. And this is where the deeper question emerges. Can time truly end? Or does it just become irrelevant when nothing meaningful happens within it? Some physicists describe this era as a state where time continues mathematically but becomes physically empty. Others speculate that without change, the arrow of time, the direction we experience from past to future, disappears entirely. Roger Penrose even proposed a framework called conformal cyclic cosmology, suggesting that an extremely empty universe might eventually become indistinguishable from the Big Bang of a new one. No matter the interpretation, imagining the end of time invites us into a landscape where physics and philosophy blend. What is time if nothing moves? What is duration if no process marks its passing? What does it mean for before and after, when the universe holds no events to anchor them? These questions aren't only theoretical, they challenge our understanding of existence itself. The entire structure of physical law depends on time. Our lives, our memories, our experiences, all rooted in the act of change. To imagine a universe stripped of that fundamental ingredient forces us to confront the strangeness of reality at its deepest level. But in this moment, as you drift in the cold quiet of the far future, the question doesn't feel abstract. It feels immediate, present. The universe has aged beyond anything familiar. The stars are gone. The galaxies have dissolved. Even the background glow of creation has stretched beyond recognition. The cosmos is entering its final state, whatever that truly means. And in this vast, frozen silence, the concept of time begins to lose its grip, not because clocks have stopped ticking, but because there is nothing left for them to measure. Here, at the horizon of everything, the end of time is not an abrupt event, but a slow fading of meaning, a gentle unravelling of change itself, and this is where our exploration begins. To understand the far future of the universe, we have to begin with the idea that time is not merely a backdrop for events. In cosmology, time moves forward because the universe changes, and the universe changes because energy redistributes. Stars burn hydrogen into helium, galaxies collide and merge, black holes swallow matter, and radiation travels outward into expanding space. These processes create an unmistakable direction, a forward flow. This direction is known as the arrow of time. It's easy to forget how central it is to our experience. A cup of hot tea cools down instead of spontaneously heating up. Smoke disperses instead of forming itself back into a perfect cigar. Stars form, shine, and die. They don't reassemble themselves from scattered ashes. The arrow of time is not a physical push, but a statistical inevitability emerging from billions of particles taking countless tiny steps toward disorder. The principle behind this is entropy, a measure of how spread out or disorganized energy is. High entropy means the universe is more evenly dispersed. Low entropy means energy is clustered, forming stars, galaxies, and all the complexity we know. Entropy always increases, not because of any law that forbids the reverse, but because the reverse is so unimaginably improbable, it effectively never happens. In the early universe, entropy was low. Matter was dense, packed into a hot primordial plasma. Over the last 13.8 billion years, the universe has expanded, cooled, and become less orderly in the large-scale sense. Galaxies cluster, but stars burn fuel irreversibly. Black holes consume matter without returning it. Every process pushes the cosmos toward states that are easier to occupy, states of higher entropy. That trend gives us a cosmic timeline that stretches far beyond humanity's existence. We are early observers in a universe that is still forming structures, still burning bright, still carrying the echoes of the Big Bang. But modern cosmology lets us extend our vision trillions of years forward. We use the laws of thermodynamics, general relativity, quantum mechanics, and observational data from telescopes to extrapolate what comes next. When physicists like Freeman Dyson, Roger Penrose, Stephen Hawking, and the duo Gregory Laughlin and Fred Adams mapped out these futures, they weren't guessing. They were following equations we can test today, on timescales we can observe today, knowing that once the rules are known, the consequences can be calculated with astonishing precision. The story cosmology tells is vast, but it begins with themes we already encounter in everyday life: heat, expansion, and the irreversible flow of entropy. Since entropy always increases, and since the universe expands, all processes that drive the arrow of time eventually lose the energy gradient they rely on. Stars will run out of fuel, gas reservoirs will be depleted, galaxies will drift apart as space itself grows, even black holes will evaporate as Hawking radiation slowly leaks out from their horizons. But before we explore these long-term outcomes, we need to look more closely at what sets the boundaries of cosmic futures, the overall shape and behaviour of the universe itself. By observing distant galaxies, scientists discovered in the late 1990s that the expansion of the universe is accelerating. Something, now called dark energy, is pushing space to expand faster over time. This unexpected discovery reshaped cosmology entirely. Before then, it was assumed that gravity might slow the expansion enough to eventually halt it. That would have made the universe prone to collapsing again someday in a dramatic reversal of the Big Bang. But dark energy changed the picture. Instead of slowing, expansion continues to speed up. Galaxies move away from one another at ever greater rates, and in the far future, the night sky from any given galaxy will become emptier and darker as everything else slips beyond the cosmic horizon. This sets the stage for three classical cosmic finales, each corresponding to a different cosmic behaviour. Heat death, big rip, big crunch. These scenarios aren't arbitrary. They reflect how gravity, dark energy, and thermodynamics play out on cosmic scales. Heat death is the simplest and has the strongest foundation in modern physics. It states that the universe will expand forever and cooling will continue until all energy is uniformly spread throughout space. When energy is perfectly dispersed and no gradients remain, nothing can happen. No stars can burn, no collisions can occur. Entropy reaches its maximum, and the universe exists in a silent, static equilibrium. This scenario emerges if dark energy is constant or nearly constant, a condition supported by current observations. In the language of cosmology, this corresponds to a cosmological constant, an unchanging energy density inherent to space itself. In this model, the expansion never stops. Galaxies drift apart, stars burn out, black holes evaporate. Eventually, matter and radiation thin so drastically that interactions between particles become almost non-existent. The result is a universe that approaches absolute zero in temperature. Not exactly zero, just unimaginably close. Kelvin temperatures so low that even the most energetic particles barely move. This is the ultimate endpoint of time as understood through thermodynamics. A state with no free energy, where entropy can no longer rise because it has reached its peak. It is, in effect, cosmic stillness. But heat death isn't the only possibility, and cosmologists haven't ignored the alternatives. One of the more dramatic ones is the Big Rip. To understand this scenario, imagine that dark energy isn't constant but grows stronger over time. This type of dark energy is called phantom energy. Instead of simply accelerating the expansion, it accelerates it so violently that eventually it overcomes not just the gravity between galaxies, but the gravity within galaxies, within solar systems, within planets, even within atoms. First, galaxy clusters break apart. Then individual galaxies, then stars, then planets. Finally, atoms themselves are torn open as the expansion becomes so extreme that even the forces binding quarks inside protons are overwhelmed. If this sounds catastrophic, it is. But there's no evidence that dark energy behaves this way. Current data fits a constant dark energy model extremely well. Still, cosmologists examine the Big Rip because exploring extreme models helps test the limits of physics. If the Big Rip turns out to be correct, the universe will end not in silence, but in a runaway expansion that leaves behind nothing but a thinning fog of fundamental particles. Even more dramatic is the reverse of the universe we see today, the Big Crunch. Before the discovery of dark energy, the Big Crunch was the leading candidate for the universe's end. If the density of matter in the cosmos were high enough, gravitational attraction could slow expansion, stop it, and eventually reverse it. Galaxies would drift back toward each other, temperature would rise, radiation would become more intense. Eventually, everything would collapse into a superheated, ultra-dense state, not unlike the conditions of the Big Bang. The cycle could potentially repeat. Some physicists suggested an oscillating universe, a sequence of bangs and crunches with no ultimate beginning or end. Penrose proposed his own variation, conformal cyclic cosmology, where each infinitely expanded, extremely cold universe transforms into the next through a mathematical rescaling of time and space. In that picture, the end of one universe becomes the birth of another. But observational evidence strongly contradicts the Big Crunch today. Dark energy seems to dominate, and matter density is too low to halt expansion. Unless dark energy changes behavior in the future, a crunch is unlikely. But the idea remains scientifically valuable because it reveals that cosmic destiny is written in the balance between gravity and expansion. To anchor our view of the future firmly in known physics, we rely on the work of theorists like Freeman Dyson. In the 1970s, Dyson explored different possible fates for life and intelligence in an ever-expanding universe. He proposed that even in a fading cosmos, life might find ways to adapt to increasingly sparse energy supplies. Though this idea faces challenges from later work, particularly the limits imposed by thermodynamics and quantum mechanics, it remains one of the earliest serious explorations of the far future. Stephen Hawking contributed significantly by studying black hole evaporation. He showed that black holes emit radiation due to quantum effects near the event horizon. Over enormous timescales, this energy loss causes black holes to shrink and eventually disappear. His work revealed that even the largest black holes, which form the gravitational anchors of galaxies today, are temporary. Meanwhile, Gregory Laughlin and Fred Adams mapped what has become the standard long-term cosmic timeline. Their calculations stretch across periods up to 10 to the 100th power years and beyond, dividing cosmic history into eras: the stelliferous era, the degenerate era, the black hole era, and the ultimate dark era. Each era reflects a different dominant physical process, from star formation to black hole evaporation to near-total stasis. What makes their work remarkable is how seamlessly they combine astrophysics, thermodynamics, and particle physics. Their models show not only when stars will die and galaxies will drift apart, but also when matter decays, when black holes evaporate, and how entropy evolves across unimaginable spans of time. Across all these contributions, From Penrose's geometric universes, to Hawking's evaporating black holes, to Dyson's speculative life strategies, to Adams and Laughlin's meticulous cosmic ledger, cosmology builds a consistent framework. While some details remain uncertain, the broad outline is robust. Unless dark energy behaves in a radically different way, the universe will expand forever, grow colder, and move toward a state of maximum entropy. The arrow of time may persist mathematically, but its meaning becomes fragile. When the universe has no gradients of energy left, time becomes hard to define operationally. It becomes a background parameter rather than a driver of events. The cosmos, once dynamic and bright, becomes a quiet, static field of particles drifting in ever-expanding space. Our present moment is not just early, it is astonishingly early. The universe today is vibrant. Stars burn, galaxies form, matter flows. Entropy increases rapidly. Time has texture, events, histories, structures, cycles, emergence. But the laws of physics point us toward a vastly different future. A future where the arrow of time weakens, not because clocks fail, but because change fades. A future where the cosmos becomes diffuse. A future where energy thins to quiet equilibrium. And in that distant silence, the meaning of time begins to unravel. Cosmology doesn't just predict the fate of the universe, it invites us to see ourselves in context. A momentary spark inside an unimaginably long journey, from low entropy to high, from concentration to expansion, from brightness to stillness. For now, the universe remains young enough to evolve, energetic enough to create, and dynamic enough to sustain structure. But the laws that govern stars, galaxies, and black holes carry us forward toward a future where those same processes slow, fade, and eventually stop. And it is in this transition, from a universe rich in gradients to one where gradients disappear, that the deepest questions about time, change, and cosmic destiny take shape. The bright, structured universe we live in today is powered by a single process: stars turning hydrogen into heavier elements. Every sunrise on Earth, every glow from a distant galaxy, every nebula illuminated by ultraviolet radiation, these are all symptoms of a cosmos still young enough to shine. But star formation is not eternal. It depends on fuel, density, and temperature, and each of those slowly changes as the universe expands. Right now, star formation is decreasing. The universe reached its peak rate roughly 10 billion years ago, during an era when galaxies were dense with cold gas and collisions were more common. Back then, nebulae collapsed into new suns with astonishing efficiency, and star clusters formed by the millions. Over time, though, much of this gas has been consumed, locked into stars, or expelled into intergalactic space by supernovae and active galactic nuclei. Today, the star formation rate is only a fraction of what it once was. Galaxies still make stars, but the process is slowing. In the far future, this decline will continue until star formation effectively stops. This is where the timeline of trillions of years begins. Timescales so far beyond the human frame that even the lifespan of our sun feels brief. The most dramatic change in the distant future is the dominance of red dwarfs. These small, cool stars are the universe's quiet workhorses. They make up the majority of stars by number, but because they're so faint, most are invisible to the naked eye, even today. Their lifespans are extraordinary. While massive stars live only millions of years and sun-like stars live billions, red dwarfs can live trillions. They burn their hydrogen so slowly and efficiently that they barely change over cosmic epochs. As brighter, more massive stars age and die, red dwarfs remain. Their slow-burning cores stretch their lifetimes to lengths that dwarf the entire history of the universe so far. While our sun will one day expand into a red giant, shed its outer layers, and leave behind a white dwarf, a typical red dwarf will continue shining long after. And because they mix their fuel so thoroughly, convecting hydrogen throughout the star, rather than burning only a core region, they use nearly all their available mass for fusion. In contrast, the Sun will burn only a small fraction of its total hydrogen before its core becomes inert. This red dwarf era begins when most Sun-like stars have faded, around tens of trillions of years into the future. Although the exact timing varies with galactic conditions, cosmologists generally place the decline of star formation and the transition into this era on timescales approaching 10 to the power of 13 to 10 to the power of 14 years. It's staggering to consider that this number is about 1,000 times longer than the universe's current age. During this era, galaxies begin to look very different from how they appear today. Without large, hot stars, there are no bright blue clusters, no ultraviolet-emitting young stellar regions, and no large-scale galactic fireworks. Instead, galaxies become collections of faint red pinpoints, each glowing gently in the darkness. Their spiral arms fade, and their structures gradually blur as stars evaporate slowly through gravitational interactions. To someone observing the night sky during this era, the cosmos would appear dim and quiet. A galaxy like the Milky Way, once a swirling disk of hundreds of billions of luminous stars, will be populated mainly by small red embers and cooling remnants of former suns. Only the most sensitive telescopes, far beyond anything humanity has constructed, would be able to detect the last bright stars. But even red dwarfs eventually run out of fuel. When they finally exhaust their hydrogen, they do not swell into giants like the Sun. Instead, they contract slightly and become hotter before slowly transitioning into white dwarfs. This process is peaceful, lacking the violent convulsions of more massive stars. A red dwarf's death is a quiet fade rather than an explosion. White dwarfs themselves are unusual objects. They are roughly the size of Earth but contain mass comparable to the Sun. Their structure is supported not by nuclear fusion but by electron degeneracy pressure, a quantum mechanical effect that resists further compression. With no fusion to replenish their heat, they gradually radiate away their stored energy into space. At first, white dwarfs glow with a steady, bright light. Over billions of years they cool, their surfaces dimming from white to orange to red, and eventually to black. A black dwarf is the theoretical final state of a white dwarf, a cold, dark, stellar remnant with no light of its own. None exist yet because the universe is not old enough for white dwarfs to have cooled that far. The coolest white dwarfs observed today still retain heat from the early universe and glow faintly. The transition from white dwarf to black dwarf takes hundreds of trillions of years, far beyond the current cosmic age. When black dwarfs become common, the night sky will be dramatically different from anything familiar. Instead of stars shining by fusion, the universe will contain countless dark cinders slowly drifting through space. These objects will be invisible except through gravity, silent witnesses of a universe that once burned brightly. Galaxy evolution during this era continues through processes that are slow but persistent. Over time, gravitational encounters between stars gradually change their orbits. Some stars gain enough energy to be ejected from the galaxy entirely, becoming intergalactic wanderers. Others sink toward the galactic center, contributing to the growth of central black holes. As star formation ceases, and galaxies lose mass through evaporation, mergers become less common. The expansive force of dark energy continues pushing galaxies apart, eventually making encounters exceedingly rare. The universe becomes a collection of isolated islands of matter floating in an ever-growing sea of darkness. Within these island galaxies, the last visible stars shine. These are the final red dwarfs, tiny suns that have rationed their fuel so efficiently that they outlive every other star type in the cosmos. Their light is weak. Many are less than 0.1% the brightness of the sun, but in a universe that has gone dark, they are among the final beacons. The end of the red dwarf era marks a profound moment in the history of the universe. It represents the fading of the last naturally shining stars. Once these stars exhaust their hydrogen and cool into white dwarfs, the cosmic night becomes permanent. The energies that once lit galaxies, created planetary systems, and drove stellar evolution will be locked away in remnants. Even then, the universe is still far from empty. Remnants of stars, white dwarfs, neutron stars, and black holes continue to evolve. But without fusion shining in the darkness, the universe enters a stage where change happens slowly. Processes unfold over timescales so vast that individual events become rare. During this long decline, thermal radiation continues to escape into space. Temperatures everywhere slide toward near absolute zero. The energy of the cosmic microwave background fades further as expansion stretches its wavelengths. On timescales of 10 to the 14th power years and beyond, the background radiation becomes nearly undetectable. One of the striking aspects of this far-flung future is the difference in how cosmic systems behave. Today, galaxies are dynamic environments. Stars orbit in spirals, nebulae collapse, supernovae explode, black holes feed, magnetic fields twist and reconnect. In the era of trillions of years, these processes slow dramatically. Galaxies flatten and disperse. Stellar remnants drift and occasionally collide, but often millions of years will pass without meaningful events. Yet even as cosmic change slows, the universe continues evolving. White dwarfs keep cooling. Neutron stars may merge or drift into black holes. Black holes themselves grow as long as matter remains for them to feed upon. And rare events, such as collisions between stellar remnants or gravitational interactions that alter orbits, punctuate the long silence. The last visible stars mark a poignant turning point. They remind us that the universe wasn't always a place of darkness. There was a time when stars formed in brilliant clusters, lighting up the cosmos with energy and warmth. But time stretches on, and even the most durable stars eventually use up their fuel. In the distant future, when the final red dwarfs flicker out and drift into their own long cooling, the universe enters a new phase, one where starlight becomes memory. Light still exists, but it is the leftover glow from earlier epochs, slowly dispersing. The timescale from now to roughly 10 to the 14th power years is dominated by the life and death of stars, especially the cooling of stellar remnants and the final glow of red dwarfs. By the end of this interval, galaxies have evolved into quiet systems filled with dark objects. The cosmos becomes colder, slower, and increasingly uniform. It is a period where the engines that powered cosmic brightness wind down, and the universe transitions from a vibrant place of formation and fusion to a quieter expanse shaped by gravity and decay. The death of star formation and the slow fading of the last red dwarfs mark the end of the cosmos as we know it, a universe no longer lit from within but drifting gently into deeper darkness. And in that darkness, the next stages of cosmic evolution begin, governed not by brilliant stars, but by the cold persistence of the remnants they leave behind. In the deep future of the universe, long after the last generation of natural stars has burned its final hydrogen and faded into remnant embers, galaxies begin to transform in ways that no living creature today will ever witness. The grand spirals that once thrived on star formation, these majestic structures filled with glowing clusters and supernovae, gradually unravel into something quieter, thinner, and far more fragile. The Milky Way, Andromeda, and every galaxy across the cosmic web will eventually dissolve, not suddenly or violently, but through slow gravitational erosion. This process, known as stellar evaporation, begins with the simple fact that stars inside a galaxy do not remain fixed in place. They orbit the galactic center, and over billions of years, gravitational encounters between stars subtly alter their trajectories. Even though the distances between stars are enormous and collisions are virtually non-existent, their mutual gravitational tugs accumulate. Each encounter acts like a tiny exchange of energy, slightly altering velocities. Some stars move inward toward the galactic core, while others gain enough momentum to drift outward. Given enough time, trillions or quadrillions of years, these small nudges add up. Some stars eventually acquire enough velocity to escape the galaxy entirely. This is not dramatic. There is no sudden launch, no explosion, no visible sign. A star simply crosses the galaxy's gravitational boundary and then continues drifting into intergalactic space. The center of the galaxy loses mass, the outer regions thin out, and the structure slowly loosens. This process is extremely slow today, almost imperceptible on human timescales, but the universe has immense patience. With trillions of years passing and the ongoing influence of dark energy accelerating the expansion of space, stellar evaporation becomes a dominant force shaping the late-time cosmos. As stars evaporate from galaxies, they enter a vast, cold expanse, where they will never meet another galaxy again. Today, galaxies occasionally collide or pass near one another, especially in clusters where gravity binds them tightly. But in the far future, cosmic expansion continues to push galaxies apart at increasing rates, eventually making encounters extraordinarily rare. The local group of galaxies, Milky Way, Andromeda, and their smaller companions, will merge early on, forming a massive elliptical galaxy, sometimes referred to as Milkdromeda. But beyond that merger, the expansion of space ensures isolation. Once galaxies drift beyond each other's gravitational influence, they become cosmic islands surrounded by darkness. Within these isolated galaxies, change continues. Over enormous spans of time, the distribution of mass becomes more and more uneven. Central black holes grow as stellar remnants, gas clouds, and occasional wandering stars fall inward. The galactic core becomes denser and hotter, while the outer regions stretch thin, losing stars to evaporation or gravitational encounters. But the evolution of galaxies does not depend only on the stars we can see. Dark matter, the invisible scaffolding holding galaxies together, plays a crucial role. Dark matter halos extend far beyond the luminous regions of galaxies, forming massive gravitational reservoirs that provide the overall shape of galactic structure. Without dark matter, galaxies would not have formed the way they did. Their rotation curves, how fast stars orbit at different distances, reveal the vast presence of unseen mass. In the far future, dark matter halos also begin to change. The primary mechanisms aren't burning or cooling, because dark matter does not interact electromagnetically. It does not radiate heat or light. Instead, the long-term evolution of dark matter comes through gravitational interactions. Over trillions of years, dark matter particles exchange energy in much the same way stars do, albeit much more slowly. This leads to a kind of dark evaporation where some dark matter particles drift outward, eventually leaving the galaxy entirely. At the same time, the gravitational potential well of the galaxy changes as stars evaporate and central black holes grow. This alters the distribution of dark matter, gradually loosening the halo. Some models suggest that dark matter may eventually become so diffuse that the halo effectively dissolves. Others indicate that heavy central black holes could retain a portion of the halo, forming dense central regions surrounded by a vast emptiness of evacuated space. Regardless of the exact mechanism, the fate of dark matter contributes to the overall dissolution of galactic structure. As the halo disperses, stars in the outer regions become less tightly bound. They drift away more easily. The galaxy becomes more porous, more fragile. Gravitational interactions weaken on cosmic scales as the universe expands. Galaxy clusters, currently dense environments with thousands of galaxies orbiting within a single gravitational well, also undergo evaporation. Just as individual stars leave galaxies, galaxies themselves can escape clusters through gravitational encounters. over immense timescales, clusters dissolve, leaving only isolated galaxies separated by distances so vast that no light or information can pass between them once the expansion accelerates beyond certain thresholds. This leads to one of the most profound transformations in the history of the cosmos, the disappearance of the cosmic web. Today, the cosmic web is a vast structure connecting galaxies and galaxy clusters with long filamentary strands of matter. These filaments span hundreds of millions of light years and contain both dark matter and gas. They formed from tiny fluctuations in the early universe that grew under gravity, creating a network of interconnected structures. Galaxies formed along these filaments like dewdrops on spider silk. In the far future, this web thins as galaxies separate, filaments stretch and disappear from view as expansion increases. Eventually, the cosmic web breaks down entirely. Instead of a universe filled with interconnected structures, the cosmos becomes a patchwork of isolated regions, each containing a single galaxy or a small remnant of one, surrounded by enormous expanses of empty space. The disappearance of the cosmic web marks the end of large-scale structure. It means that the universe, once governed by the competition between gravitational attraction and expansion, becomes dominated entirely by expansion. Regions that once influenced each other gravitationally become unreachable. Light emitted by one galaxy will never reach another. Information becomes permanently trapped within cosmic horizons. This isolation has profound implications for the future of matter. Without the gravitational influence of neighbouring galaxies or filaments, internal interactions in each galaxy continue at a slower pace. Stars evaporate, dark matter disperses. Over time, the remaining matter of each galaxy becomes increasingly sparse. Eventually, a galaxy resembles a faint cloud of stellar remnants with a dense central black hole. But even this structure will not last forever. The slow gravitational interactions between stellar remnants lead to additional evaporation. Black holes may merge with or consume nearby remnants, but the overall number of objects decreases. On timescales of 10 to the 15th power to 10 to the 19th power years, many galaxies lose so many stars that their remaining material can barely be called a structure. What remains may be a loose association of black dwarfs, neutron stars, and black holes drifting through space. Meanwhile, expansion continues. Every object becomes more isolated. The universe grows darker and colder. Eventually, even the central black holes, which once anchored galaxies and influenced stellar orbits on truly cosmic scales, become dominant only by mass, not by luminosity. Their presence is invisible except for their gravitational pull. The remnants of galaxies orbit these silent centers until gravitational interactions eject them or send them inward to their final fate. By the time the cosmic web has fully dissolved, the universe holds almost no luminous objects. The few remaining stars are red dwarfs in their final moments, or rare collisions that briefly ignite faint flashes. But these events are extraordinarily infrequent. For most of the remaining matter, darkness becomes permanent. The universe that emerges from this slow evaporation is a place where the night sky, if night still had meaning, contains almost no stars. The familiar galaxy shapes of the early universe are gone. The cosmic web is gone. What remains are isolated pockets of matter drifting in an expanding ocean of near-nothingness. And yet, even then, the story is not one of absolute emptiness. It is a universe still shaped by the persistence of physics, gravity pulling remnants inward, expansion pushing everything outward, black holes holding brief dominion, and dark matter gradually fading into obscurity. But the grand architecture that once connected everything, the webs, filaments, clusters and spirals, has vanished. The cosmos becomes mostly dark, not as a metaphor but as a physical truth. Darkness becomes the dominant state, broken only by the faintest embers of dying remnants and the distant whisper of radiation stretched thin by expansion. what was once a universe full of structure becomes a diffuse, nearly featureless expanse, and within this vast quiet, the slow evolution of matter continues, governed now by decay, evaporation, and the final stages of gravitational weakening. It is the beginning of a cosmic era where the universe increasingly resembles a desert of particles and lonely objects, spread across an ever-growing space, guided by laws that never stop but gradually lose the ability to create anything new. As the universe drifts deeper into its long twilight, the familiar era of stars and galaxies gives way to a stranger chapter in cosmic history, one in which black holes become the central players. They are the final titans of structure, the last massive objects capable of shaping their surroundings. The universe transitions from being a place dominated by light and fusion to one governed almost entirely by gravity and darkness. Black holes, once the rare endpoints of massive star deaths, eventually become the dominant structures because everything else grows faint or drifts away. Stars fade, white dwarfs cool, neutron stars remain quiet, gas clouds disperse, dark matter halos evaporate, and galaxies themselves unravel slowly, losing stars through gravitational interactions and expansion. In this thinning universe, black holes remain. They do not require fuel to exist. They do not cool in the ordinary sense. They simply persist, anchored only by mass and curvature. This long era begins after the last natural stars burn out, when the luminous contents of galaxies have grown dim and the universe has entered a quiet, cooling state. The black hole era spans extraordinary timescales, up to around 10 to the 100th power years, dwarfing the entire history of the universe from the Big Bang to today. Everything before this moment becomes a prologue to the Dark Age ruled by these gravitational giants. Early in this era, the most dramatic events are the mergers of supermassive black holes. When galaxies collide, and in the early trillions of years of the cosmos, this still occurs occasionally, their central black holes spiral toward each other. Friction with surrounding stars and gas brings them together, and gravitational waves carry away energy so that they can finally merge. These events are powerful enough to send ripples through space-time across billions of light-years. The final fate of our own galaxy, once merged with Andromeda, involves such a collision. The two central black holes will eventually form a binary system, orbiting one another for millions, perhaps billions, of years before gravitational radiation draws them together in a violent but silent union. Other galaxies that remain gravitationally bound to ours may contribute additional mergers, building an even larger black hole at the centre of the remnant galaxy. In clusters of galaxies where dozens or even thousands of galaxies orbit within a single gravitational well, the central black holes can merge into even more massive entities. Theoretical models suggest black holes with masses of trillions of suns may exist in these early states of cosmic collapse and consolidation. But mergers are rare in later epochs, once dark energy has pushed galaxies apart. After the last gravitationally bound groups coalesce and all galactic mergers cease, supermassive black holes become solitary monarchs in each isolated region. They remain as the only large-scale structures capable of interacting meaningfully with their surroundings. For a long time, black holes continue to accrete material. Gas, dust, and wandering stellar remnants gradually fall inward. Occasionally, compact objects, like neutron stars or black dwarfs, spiral towards the centre after losing energy through gravitational interactions. These events are rare on human timescales but consistent across trillions of years. Still, accretion eventually dwindles. Most of the material that can fall into black holes does so early in the black hole era. As galaxies dissolve and stars evaporate into intergalactic space, the supply of matter shrinks. Gravitational encounters become infrequent. The universe expands further, making isolated black holes ever more lonely. Once accretion stops and galaxies dissolve, black holes become quiet. Their event horizons remain cold and dark. Outside their boundaries, space grows progressively colder, approaching temperatures near absolute zero. Without fresh material to heat, without the radiation of active accretion disks, black holes become almost invisible. But despite their seeming stillness, black holes are not eternal. Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit radiation. This Hawking radiation is extraordinarily weak for large black holes. A supermassive black hole with the mass of a galaxy's central object might take up to 10 to the power of 100 years to evaporate completely. Smaller black holes evaporate first, followed by progressively larger ones. Hawking radiation arises from particle-antiparticle pairs that form spontaneously near the event horizon. Normally, such pairs annihilate quickly, but near a black hole, one particle can be captured while the other escapes. To an outside observer, it appears as though the black hole emits radiation. The escaping particle carries energy away, gradually reducing the mass of the black hole. Early in the black hole era, this radiation is negligible. For a black hole with the mass of the Sun, the evaporation time is about 10 to the 67th power years. For a black hole a billion times larger, the timescale increases accordingly. In the early trillions of years, Hawking radiation plays almost no role. But as the universe grows colder and emptier, even such faint processes become significant. Black holes gradually lose mass. Their temperatures increase as they shrink. The smaller a black hole is, the hotter it becomes. Late in the era, when a black hole has lost most of its mass, Hawking radiation intensifies dramatically. The final moments are violent on atomic scales. The black hole radiates energy in a burst of high-energy particles, releasing more light in the last fraction of a second than in the entire span of its existence up to that point. Even so, these bursts would be almost undetectable, lost in a universe that has grown too large and dark for any observer to register them. As black holes evaporate, they leave behind clouds of radiation, photons, neutrinos, and other particles that gradually disperse into the expanding cosmos. These particles drift outward, stretched into longer wavelengths by the ongoing expansion. Over unimaginably long timescales, any energy released by evaporating black holes becomes diluted until it is effectively indistinguishable from the faint background of the cosmos. On timescales approaching 100 billion years, the last of the supermassive black holes begins its final evaporation. These black holes started as the giants at the centres of galaxies, consuming stars and gas until little remained. Over the trillions and quadrillions of years that followed, they grew colder, darker, and more isolated. Now in the final eons of their existence, they begin to glow faintly with Hawking radiation. If there were observers in this era, which is almost impossible given the conditions, they would witness a universe filled with lonely black holes emitting tiny amounts of radiation. These final black holes would be the last significant structures in a universe that has grown almost entirely featureless. Even the cosmic microwave background, once brilliant and energetic, has long since stretched into wavelengths larger than entire galaxies. The universe is dark, not because light doesn't exist, but because it is so diffuse that it cannot illuminate anything. The evaporation of the final black hole marks the end of large-scale structure in the universe. After that moment, the cosmos enters a state of near-total uniformity. No galaxies, no stars, no black holes, only a very thin distribution of particles and radiation across an unimaginably vast expanse. What remains of matter and energy continues to disperse. On these timescales, even rare interactions, such as occasional particle collisions, become so infrequent that entire regions of space can go without any meaningful event for periods longer than today's age of the universe multiplied by trillions. In this quiet, drifting sea of particles, the meaning of event becomes unclear. Time is still defined in the mathematical sense, but without processes to mark transitions from one moment to another, its physical relevance diminishes. The universe has entered a state where change happens so slowly and so rarely that time becomes something abstract, detached from experience. And yet, even in this nearly featureless future, the legacy of black holes lingers. They shaped the evolution of galaxies, consumed matter, released gravitational waves, and finally faded through quantum processes. For a significant fraction of the universe's lifespan, they were the dominant structures, the last giants of a cosmic landscape that once burned bright with starlight. Their reign ends not with a crash or a collapse, but with a whisper of radiation fading into an ever-expanding darkness. The universe continues along its slow path toward greater entropy, guided by processes so subtle and slow that they stretch the imagination to its limits. In the vast timeline of the cosmos, the black hole era marks the final moment of complexity. After the last black hole evaporates, the universe moves into a state of profound simplicity, an ocean of particles drifting apart in a space that expands without end. This is the legacy of a universe that once thrived with galaxies, stars, and life. And now, with the departure of its last great structures, the cosmos settles deeper into its quiet, dark future. Black holes are often imagined as eternal, unchanging abysses, silent anchors in a universe that slowly falls apart. For most of cosmic history, that picture is close enough to be true. They swallow matter, curve space-time, and remain stable for extraordinary lengths of time. Yet in the farthest reaches of the future, when galaxies have dissolved and stars have faded, black holes themselves begin to change. Not because anything falls into them, but because of something far more subtle, the quantum structure of empty space around their horizons. This phenomenon, Hawking radiation, transforms black holes from seemingly immortal objects into slowly evaporating bodies. It ties together general relativity, quantum field theory, and thermodynamics in one of the most remarkable predictions ever made about the universe. To understand why black holes evaporate, we must look closely at the nature of empty space. In classical physics, a vacuum is simply nothing, but quantum mechanics says otherwise. The vacuum seethes with activity. It is filled with transient particle-antiparticle pairs that flicker into existence and annihilate almost immediately. These particles arise from quantum fluctuations, which are allowed by the uncertainty inherent in space-time itself. Near a black hole's event horizon, the boundary beyond which nothing can escape, these fluctuations behave differently. If a particle-antiparticle pair appears exactly at the horizon, one member can fall inward while the other escapes outward. If the escaping particle moves away from the black hole, it becomes real rather than virtual. To conserve energy, the black hole loses a small amount of mass. Over time, this steady loss accumulates, and the black hole evaporates. This process is staggeringly slow for large black holes. For a black hole with the mass of our Sun, the evaporation time is around 10 to the 67th power years, far beyond the lifetimes of stars, galaxies, or even most structures in the universe. For supermassive black holes, the timescale is even more extreme. A black hole with 1 billion solar masses takes roughly 10 to the power of 99 years, nearly stretching to the theoretical limit of the black hole era. But despite these enormous numbers, Hawking radiation is relentless. Once accretion stops and the universe grows cold, black holes no longer gain mass. Instead, they radiate it away. The larger the black hole, the colder it is, and the slower the process. Small black holes radiate quickly, but also cool down rapidly as they shrink. When a black hole becomes small, its temperature rises dramatically, accelerating its evaporation. Black holes, therefore, have a kind of thermal life cycle. In the early universe, they glow exceedingly faintly, far too weak for any current technology to detect. A stellar mass black hole today would emit a temperature far below the cosmic microwave background, making the surrounding universe warmer than the black hole itself. This means black holes currently absorb more radiation than they emit, growing slowly. But as the universe expands and cools, a turning point arrives. the cosmic background temperature drops below the temperature of the black hole. After that, the black hole becomes warmer than the universe and begins to lose mass. Over time, the evaporation becomes irreversible. In the far future, when the universe is unimaginably cold and nearly empty, Hawking radiation becomes the dominant effect shaping black holes. For trillions upon trillions of years, black holes shrink quietly, emitting low-energy particles, photons, neutrinos, and eventually heavier particles once the temperature rises enough. The timeline of evaporation varies by black hole size. Stellar mass black holes. These are the relics of massive stars, objects a few times the mass of the Sun. They evaporate over timescales from 10 to the power of 67 to 10 to the power of 70 years. The radiation they emit is faint and low energy for almost all of their existence. Only in their final moments does the process accelerate dramatically. In the last few seconds, a stellar mass black hole shrinks rapidly. Its temperature skyrockets. The radiation becomes intense, producing a last burst of high-energy particles. This final flash briefly outshines the entire history of the black hole's emission, then fades instantly as the black hole disappears. Intermediate mass black holes. These black holes, ranging from hundreds to thousands of solar masses, are rarer and potentially form through stellar mergers or dense star cluster collapse. Their evaporation times span roughly 10 to the power of 70 to 10 to the power of 78 years. They pass through long, quiet epochs when the surrounding universe is almost entirely inert. For most of this time, their existence is defined not by activity but by stability. Only after eons of shrinking do they reach a stage where Hawking radiation becomes significant. When they do, their final bursts are more energetic than those of stellar mass black holes, releasing vast quantities of particles in their last instant. Supermassive black holes. These are the giants of the cosmos, millions or billions of solar masses, formed from the collapse of early galaxies, mergers, and accretion of matter. The evaporation time of a supermassive black hole is staggering, up to 10 to the power of 99 or even 10 to the power of 100 years. This is near the upper limit of any meaningful timeline for cosmic processes. For nearly all of those years, these black holes do not change. They sit in silent isolation, surrounded by a universe that has cooled below a trillionth of a degree above absolute zero. Their radiation is unimaginably faint. A supermassive black hole of 1 billion solar masses has a temperature so low that even the current universe, with a temperature of about 2.7 Kelvin, is far too warm for evaporation to begin. Only after the entire cosmic background radiation has been stretched by expansion into wavelengths larger than the observable universe does Hawking radiation overtake absorption. At that point, the black hole begins to shrink. Slowly at first, and then with increasing speed. By the time a supermassive black hole reaches its final moments, the universe around it is a nearly perfect vacuum. A few particles per unimaginable volume of space drift silently among photons with wavelengths spanning light years. The black hole's temperature rises to incredible levels, and in the final fraction of a second, it unleashes an enormous burst of radiation. This final explosion is the last significant energetic event in the universe. It releases the remaining mass energy of the black hole in a brilliant flash, though brilliant here is relative. There are no observers, no galaxies, no nearby matter to illuminate. The burst expands freely into an empty, dark cosmos, stretching out, cooling and thinning until it becomes indistinguishable from the faint bath of particles that fills space. This marks the end of the largest black holes. When they evaporate, there are no more gravitational giants. The universe no longer contains anything capable of forming new structures or collapsing matter inward. The black hole era gives way to an even quieter epoch. One defined not by mass, but by the slow drift of radiation and isolated particles. As the universe continues expanding, these particles spread out farther. Waves stretch, energies diminish. Collisions become so rare that entire regions of space may go without a single interaction for unfathomable lengths of time. What makes Hawking radiation remarkable is that it ties the ultimate fate of the universe to phenomena that originate at the smallest scales of reality. Quantum fluctuations, tiny, constant rearrangements of the vacuum, drive the final dissipation of the largest structures in existence. Black hole thermodynamics, a field blending ideas from general relativity and statistical mechanics, tells us that black holes have entropy, temperature, and energy flow, much like more familiar systems. A black hole's entropy, for example, is proportional not to its volume, but to the area of its event horizon. This suggests that the information content of a region of space might be encoded on its boundary, an idea that led to the holographic principle, one of the most influential concepts in theoretical physics. Though the full implications of this connection remain debated, it shows how the physics of black holes reaches far beyond astrophysics and extends into the foundations of reality itself. The evaporation of everything through Hawking radiation also emphasizes how deeply time and thermodynamics are intertwined. The increase of entropy drives physical processes forward. The evaporation of black holes increases entropy dramatically, accelerating the universe toward a final state of maximum disorder. And yet, despite its bleakness, the slow fading of black holes is a testament to the persistence of physical law. Even in a universe devoid of stars, galaxies, and matter, the interaction between gravity and quantum mechanics continues, inexorably shaping the cosmos. In the end, the universe becomes a place without structure, without complexity, and without the gravitational anchors that once defined cosmic evolution. The final bursts of evaporating black holes are the last echoes of the universe's most massive objects. After they disappear, the cosmos becomes an ocean of low-energy particles drifting through an expanding, near-empty space-time. In this profound quiet, the last light fades, not with violence, but with the steady, patient work of quantum fluctuations erasing the final remnants of structure. The slow evaporation of everything is not simply an ending, it is the universe completing the long arc of thermodynamic evolution. What began as a hot, dense explosion of low entropy gradually becomes a cold, diffuse expanse where entropy has reached its maximum. The story of black holes, these enormous engines of gravity, ends with a whisper of radiation, leaving behind the faint traces of a cosmos that once was bright. After the last black holes begin their long fade through Hawking radiation, the universe still contains something familiar: matter. Even in the emptiest reaches of the far future, protons remain, frozen, inert, drifting across expanses so large that interaction becomes nearly impossible. For most of cosmic history, protons have been the backbone of ordinary matter. Every atom of hydrogen, every neutron star, every whisper of interstellar gas relies on them. They have endured supernovae, cosmic rays, the early plasma of the Big Bang, and trillions of years of cooling expansion without showing signs of decay. But particle physics suggests that this apparent immortality might not last forever. If protons are unstable, the far future of the universe changes dramatically. Instead of a cosmos filled with long-lived remnants, white dwarfs, neutron stars, planets, and cold atoms, matter itself dissolves. The universe transitions into a thin haze of leptons and radiation. The atomic world, which has defined the visible universe from the first moments after the Big Bang, eventually disappears. To understand this possibility, we look to theories that extend beyond the standard model of particle physics, the grand unified theories, or GUTS. These models aim to unify the strong, weak, and electromagnetic forces, three of nature's fundamental interactions, into a single framework. In these unifications, the separate forces we see today are just manifestations of one deeper force that existed at extremely high energies, such as those present in the first fractions of a second after the Big Bang. One striking prediction of many GUT models is proton decay. In the standard model, protons are stable. They have no allowed decay pathways. But in guts, new interactions become possible. These interactions allow quarks, the fundamental building blocks inside protons, to convert into leptons, such as positrons or neutrinos. If such a conversion can happen, the proton is no longer permanent. The predicted lifetimes for proton decay are enormous. Many models predict half-lives around 10 to the 34th power years. Others extend as far as 10 to the 36th power or even 10 to the 40 power years. These numbers dwarf the current age of the universe and make proton decay almost impossible to observe directly. Yet, even with these unimaginable timescales, the implications are enormous. If protons eventually decay, all structures made of ordinary matter gradually disintegrate, not by sudden collapse, but through individual particles quietly fading into lighter forms. A proton in a hydrogen atom might turn into a positron and a neutral pion. The positron annihilates with an electron, producing photons. The neutral pion decays quickly into gamma rays. Over incredibly long stretches of time, entire atoms decompose in this way. In the far future, if proton decay is real, no form of matter survives. Planets crumble into radiation. Brown dwarfs fade into electron-positron annihilation. Even neutron stars, which are packed with neutrons rather than protons, eventually decay because neutrons are made of quarks too, and are slightly heavier versions of protons. The decay of neutrons in isolation is well known, but in neutron stars they remain stable due to gravitational pressure. Yet even there, if the underlying quarks are unstable, the neutrons will also decay through similar gut processes. Supersymmetry, another major extension of the standard model, also predicts proton decay, though the details differ. Supersymmetric models propose that every particle has a heavier partner, and the interactions between these partners and ordinary matter can produce new decay channels. Supersymmetric guts therefore extend the possible half-lives and introduce new pathways for protons to disappear. Many of these models predict proton lifetimes closer to 10 to the 36th or 10 to the 38th years. The challenge, of course, is proof. Since the predicted lifetimes are so vast, experiments are designed not to watch a single proton, but to observe enormous numbers of them simultaneously. Large underground detectors such as Super Kamiokande in Japan contain tens of thousands of tons of water. They monitor an immense number of protons by looking for the telltale flashes of Cherenkov radiation that accompany specific decay products. So far, no proton decay events have been detected, pushing the experimental lower bounds to roughly 10 to the power of 34 years. The absence of detection does not rule out decay, it simply means proton lifetimes, if finite, are longer than current experimental sensitivity. At the same time, physicists remain cautious. The standard model predicts absolute stability, so experimental silence is consistent with both scenarios. If the proton is stable, much of the far future universe remains as matter. If unstable, a very different future unfolds. To imagine this alternative future, picture a black dwarf, a cooled white dwarf composed mostly of carbon and oxygen. After trillions of years, its temperature approaches absolute zero, but its structure remains. However, if proton decay occurs, atoms inside the black dwarf begin to disappear. Slowly, atom by atom, the carbon nuclei break apart. A black dwarf that once contained billions upon billions of protons loses them one at a time over unimaginable timescales. Eventually, the structure weakens and collapses into a tenuous cloud of leptons and gamma-ray photons. This is not a destructive explosion, but a gradual unwinding of matter's internal architecture. Over 10 to the 35th power to 10 to the 40th power years, the black dwarf dissolves. The process is slow enough that the object never melts in any conventional sense. Instead, it simply ceases to exist. Planets undergo the same fate. A planet like Earth, frozen and drifting in an almost empty universe, will slowly evaporate, not from heat, but from the decay of its protons. Its mass gradually transforms into radiation. After enough half-lives, no trace of the planet remains. Even neutron stars are vulnerable. Though composed mostly of neutrons, the decay of their constituent quarks leads to a breakdown of their structure. Neutrons may convert into lighter particles, releasing radiation and reducing the star's mass. Over tens of trillions of years, neutron stars dissolve as well. This process creates a universe in transition, from one dominated by matter to one dominated by radiation and leptons. The remnants of protons include positrons, neutrinos, electrons, and photons. These particles drift apart as the universe continues expanding. No stable nuclei remain, no atoms survive. The chemical complexity that once formed stars, planets, and life disappears entirely. By the time proton decay completes its work, the universe becomes a sparse bath of radiation. Energy is still present, but it spreads farther and grows colder as expansion stretches wavelengths. The distinction between matter and radiation begins to blur. The universe becomes a thin fog of low-energy particles dispersed across unimaginable distances. This picture is dramatically different depending on whether protons decay or remain stable. If stable, matter persists indefinitely, forming black dwarfs, neutron stars, and other remnants that survive far into the dark era. If unstable, matter is temporary. The atomic world is only a brief chapter in cosmic history, lasting perhaps a few dozen orders of magnitude more time than the current age of the universe, but still finite. The existence or absence of proton decay also influences the thermodynamic fate of the universe. Matter with mass has gravitational effects. If protons are stable, gravitational interactions among remnants continue shaping the late universe, however slowly. If protons decay, gravity loses almost all of its influence. The universe becomes a radiation-dominated sea, gradually stretching and diffusing into near nothingness. Experimental limits today tell us that if proton decay happens, it must be extraordinarily rare. Yet the theoretical motivations behind it remain strong. The unification of forces, the structure of supersymmetric models, and the mathematical elegance of gut frameworks all point to a universe where matter is not eternal. The picture this paints of the far future is both startling and profound. The familiar world, built from stable atoms and enduring nuclei, may be only a temporary phase. In the deepest future, the universe may not contain atoms at all. It may not contain stars, planets, or remnants. Instead, it becomes a place where matter has become radiation, where the very definition of substance dissolves. If proton decay is real, it means that everything physical slowly transforms into light or into the faintest particles. And if matter dissolves into these final forms, the universe becomes a place where the structure once provided by atoms is replaced by an almost featureless field of particles and energy. In that vision, the story of the universe is not just the fading of stars or galaxies, it is the fading of matter itself. The very building blocks of reality gradually unwind until nothing remains but a quiet haze drifting through an ever-expanding cosmos. This possibility, though still theoretical, reveals how particle physics reaches across the deepest spans of time, shaping not just the early universe but also its most distant future. The long-term fate of everything may depend not on stars or black holes, but on the stability of the smallest particles the universe has ever made. If protons turn out to be perfectly stable, if the smallest components of atomic nuclei never unravel, then the far future of the universe becomes stranger than the version shaped by proton decay. Instead of atoms dissolving into radiation, matter persists, not in the familiar form of warm planets or shining stars, but in a twilight landscape ruled by stellar remnants, gravitational drift, and the quiet persistence of quantum mechanics. Time stretches, and with it the endurance of matter itself. This era, known as the degenerate era, begins after the last red dwarfs exhaust their fuel and fade into darkness. With star formation long gone and no fresh sources of luminosity, the universe becomes filled with cold remnants, white dwarfs, neutron stars, black dwarfs, and planets cooled to temperatures only a fraction above absolute zero. These objects drift in galaxies that are themselves slowly dissolving, surrounded by expanding space that grows colder and darker with each passing trillion years. Even though the universe is no longer lit by fusion, it remains far from static. Processes governed by gravity, particle interactions, and quantum effects continue to reshape the cosmic landscape across unimaginable timescales. One of the subtle transformations involves dark matter. Although dark matter does not interact with light, its gravitational influence remains essential. It helps maintain the structure of galaxies long after the luminous matter has faded. But the long-term fate of dark matter depends on its microphysical nature. If dark matter is made of particles that can annihilate with each other, such as weakly interacting massive particles, WIMPs, then annihilation events gradually reduce the total amount of dark matter in galaxies. Early in the universe, these annihilations were common enough to influence structure. In the far future, they become rare but not non-existent. Over timescales reaching 10 to the 20 years or more, dark matter annihilation slowly thins the halos surrounding galaxies. Each event converts dark matter mass into visible radiation, photons and other high-energy particles. These flashes are faint and sporadic, but they continue until the density of dark matter becomes extremely low. With less dark matter to hold galaxies together, the gravitational scaffolding weakens. As the halo evaporates, stars and remnants become more easily unbound. Over trillions of years, galaxies evaporate as individual remnants drift out into intergalactic space. The degenerate era is one of gradual erosion, as gravity loses its influence and structure breaks apart. While dark matter thins, another surprising process may occur among the white dwarfs scattered throughout these aging galaxies. A white dwarf, even one cooled into a black dwarf, is supported by electron degeneracy pressure, the quantum pressure created when electrons are packed so tightly they cannot occupy the same quantum state. For billions or trillions of years, this pressure keeps the star stable. But quantum mechanics opens a strange possibility: quantum tunneling. This phenomenon allows particles to pass through barriers they should not be able to cross. Over extremely long timescales, tunneling can enable fusion reactions to occur even in environments far too cold for thermal fusion. Heger, Woosley and collaborators explored this possibility in 2013. Their study suggested that black dwarfs, once white dwarfs that have cooled to near absolute zero, might still experience rare quantum tunneling events that ignite fusion. The numbers are vast. The timescales for such ignition are around 10 to the power of 100 years, or even longer. These numbers defy ordinary comprehension. They represent durations so long that the entire history of the universe up to today is insignificant in comparison. But given enough time, the improbable becomes inevitable. A black dwarf made mostly of iron, carbon, or oxygen may undergo a tunneling event that allows two nuclei to fuse. This tiny spark can initiate a chain reaction, producing enough energy to collapse the dwarf and trigger a supernova-like detonation. These events would be the last supernova in the universe, rare, isolated flashes occurring in a cosmos otherwise devoid of light. These explosions do not ignite the dwarf into renewed longevity. Instead, they collapse it into a black hole. This quiet transformation, occurring only once across trillions of dwarfs and only after timescales that make all human history vanish into irrelevance, illustrates a profound truth. Quantum mechanics still shapes the universe even when all other processes have ended. If protons are stable, then many objects survive indefinitely. Planets, asteroids, iron-rich remnants. Yet quantum tunneling offers a path by which even these stable structures can eventually collapse. Though the probability is overwhelmingly small, time is overwhelmingly long. over infinite durations, even impossible events happen. Another possibility involves quantum tunneling collapse of large stellar remnants. Neutron stars, which are supported by neutron degeneracy pressure, may eventually tunnel into black holes. This process is similar to the ignition of black dwarfs, but occurs through different particle interactions. Neutrons are not fundamentally stable outside nuclei, but within neutron stars, the pressure stabilizes them. Over unimaginable spans of time, quantum tunneling might allow neutrons to combine or convert in ways that destabilize the star. The result would be a sudden collapse into a black hole, releasing a burst of energy before the object becomes quiet forever. These collapses, like the ignition of black dwarfs, would be rare events scattered sparsely across a vast, dark universe. Still, most of the matter in the degenerate era remains cold and inert. Planets become frozen spheres. White dwarfs fade. Black dwarfs linger. Neutron stars drift. These objects orbit galaxy remnants or float independently through space. They do not shine. They do not collide often. Their existence is defined by silence and stability. The stability of matter transforms the degenerate era into a slow-moving landscape, almost static, but never quite motionless. Gravity continues to work, though weakly. Objects still orbit one another, though on trajectories altered by encounters separated by trillions of years. Occasionally, two remnants pass close enough to exchange gravitational energy, sending one drifting away and forcing the other inward. This slow evaporation of remnants continues for enormous durations. Galaxies dissolve, not in a dramatic collapse, but through the persistent accumulation of tiny interactions. Over 10 to the 20 to 10 to the 40 years, the last remnants slip away into intergalactic darkness. Throughout this time, the universe continues expanding. Space stretches, radiation thins, temperatures sink toward absolute zero. But if protons are stable, matter never dissolves entirely. The universe becomes a cold archive of everything that once existed. Stellar cores, frozen planets, iron-rich remnants drifting through a vacuum with almost no interactions. Dark matter, meanwhile, has almost completely annihilated if it is made of self-annihilating particles. If not, it continues drifting as well, providing a gravitational influence but contributing little else. The degenerate era, then, is not a static end state. It is a long, slow unwinding of gravitational structures and quantum processes. Everything that once shone becomes dark. Everything that once burned becomes cold. Yet matter endures, preserved by the stability of protons and the slow resistance of quantum pressures. Toward the end of this era, most compact remnants have either drifted into black holes or become isolated objects lost in expanding space. A few black dwarfs ignite through tunneling, a few neutron stars collapse, but these events are incredibly rare and grow rarer as time moves on. The horizon of meaningful events stretches so far into the future that the universe becomes a place where almost nothing happens, yet the ongoing potential of quantum mechanics ensures that almost anything can still happen, given enough time. The degenerate era paints a picture of the universe defined not by light or heat, but by endurance. If protons do not decay, matter refuses to vanish. Instead, it persists in its coldest, most condensed states, drifting slowly through a cosmos whose expansion never stops. And in that persistence, the universe carries the remnants of its earlier brightness. White dwarfs turned black, neutron stars dim and quiet, and the occasional quantum spark that reminds us that even in near-eternal darkness, the laws of physics continue to operate. As the universe stretches deeper into its far future, its last sources of natural brightness begin to vanish. The long era of stars has passed. The epoch of black holes has ended. What remains is a universe entering a state that is almost difficult to describe in human terms. A cosmos without meaningful light. The last photons produced by stars faded long ago. Even the faint afterglow of black hole evaporation, the final flashes released in the ultimate instance of Hawking radiation, disperse quickly into the expanding vacuum. When these photons finally stretch beyond wavelengths capable of interacting with anything, the universe becomes effectively lightless. Not because photons no longer exist, but because their energy has been diluted to the point of near irrelevance. The expanding universe stretches every photon's wavelength, lowering its energy until it becomes so faint and so long that it carries almost no capacity to heat, excite, or illuminate anything. The darkness of this era is not like the darkness between stars today. Modern cosmic darkness is full of potential light, starlight from distant galaxies, the glow of nebulae, and the ever-present cosmic microwave background. Even the shadows of the present universe exist within a sea of photons. But the future darkness is different. It is the darkness of a cosmos where light itself has been stretched into invisibility. To understand what this means, consider the temperature of the universe. Today, the cosmic microwave background, CMB, has a temperature of about 2.7 Kelvin, or roughly minus 270.45 degrees Celsius, minus 454.81 degrees Fahrenheit. As the universe expands, this temperature decreases. The wavelength of the background radiation grows, becoming longer and cooler over time. The cooling is relentless. At 0.1 Kelvin, about minus 273.05 degrees Celsius or minus 459.49 degrees Fahrenheit, the average photon's wavelength is roughly 3 times the size of the solar system. After trillions of years more expansion, when the temperature drops to 10 to the minus 10th Kelvin, about minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit, the wavelength will exceed the size of a galaxy. Eventually, the universe cools to temperatures so close to absolute zero that even the concept of temperature loses meaning. The difference between, say, 10 to the minus 30 Kelvin, negative 273.15 degrees Celsius, negative 459.67 degrees Fahrenheit to the nearest hundredths, and true zero becomes functionally irrelevant. The motions of particles slow to a near halt. Interactions become extremely rare. Radiation loses most of its ability to influence matter. At these temperatures, even the faint photons from the last black holes are stretched to lengths greater than the current observable universe. They no longer behave like light in any intuitive sense. A single photon might exist as a wave whose crest-to-crest distance is measured in trillions of light-years, larger than any region that could meaningfully intersect with matter. This is the moment the universe becomes lightless, not merely visually, but physically. Light no longer participates in the story of the cosmos. The cooling of the universe has another consequence, the ultimate dilution of matter. Even if protons remain stable, the density of particles becomes extraordinarily low. In the early universe, matter was dense enough to form stars and galaxies. During the age of galaxies, matter remained clumped enough to maintain clusters. But in this far future darkness, the density of matter becomes so low that you could define a region of space 1 trillion light-years across and still find it nearly empty. Particles exist but rarely. A lone electron or neutrino might drift through space for ages without encountering another. The expansion of the universe ensures that whatever matter remains becomes separated across distances so vast that interaction becomes physically impossible. Even gravity grows weaker on these scales, not because gravity itself changes, but because the distances between masses grow so enormous that gravitational influence fades into insignificance. The cosmic microwave background, once brilliant, becomes stretched to wavelengths beyond any meaningful physical scale. It no longer resembles radiation as we know it. It becomes a uniform, low-energy field, indistinguishable from the vacuum. The idea of background itself becomes abstract, since there is nothing left to contrast it with. In this era, the universe is not exactly empty, but it behaves as if it is. Everything is spread so thin that the cosmos becomes a kind of near-perfect vacuum. The rare particles that remain drift with incredible inertia. Their velocities may be tiny, but given enough time, even these motions carry them across incomprehensible distances. And because interactions are almost non-existent, each particle essentially experiences the universe in complete solitude. Some remnants from earlier ages still exist. Cold black dwarfs, stellar remnants once bright with fusion, may remain if protons are stable. Neutron stars, if not subject to quantum tunneling collapse, persist as dense but silent masses. Planetary remnants drift, frozen to temperatures infinitesimally above absolute zero. But these objects, too, are isolated. With galaxies dissolved and most gravitational bonds broken by expansion, each remnant becomes an island in a cosmic ocean. Bound systems that once survived the dissipation of galaxies eventually decay through minute interactions or gravitational nudges. Over enough time, even stable orbits become unstable. The concept of illumination loses meaning. A starless universe has no shadows, but in this era, it also has no light to cast them. A black dwarf, drifting through darkness, emits nothing. A neutron star no longer shines. The only illumination comes from the occasional decay of unstable particles, rare flashes that have no witnesses and no effect on their surroundings. The faintest radiation produced from particle interactions continues to stretch and fade. When the universe cools to temperatures near 10 to the minus 40 Kelvin, still minus 273.15 degrees Celsius and minus 459.67 degrees Fahrenheit in practical terms, any photon produced at this time would have a wavelength vastly larger than the observable universe. Its energy would be so diluted that it would effectively never interact with anything. This is what the universe looks like when light has been stretched beyond usefulness. The grand structures of earlier ages, galaxies, clusters, filaments, are gone. Even isolated black holes have evaporated. The universe becomes a nearly featureless expanse where the distinction between something and nothing becomes subtle. A particle drifting in this void does not perceive darkness because there is no perception. Darkness becomes the environment itself, not a lack within it. The temperature of the universe asymptotically approaches absolute zero, while absolute zero, 0 Kelvin, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit, is theoretically unreachable for thermodynamic reasons. The cosmos comes close enough that no macroscopic physical difference remains. Thermal motion becomes essentially non-existent. Reactions cease. The dance of particles that once defined the universe's evolution slows to nearly complete stillness. Yet even here, in this almost static expanse, physics continues quietly. Quantum fluctuations never stop. Space remains dynamic at the smallest scales. Virtual particles appear and vanish, though these events become even more ephemeral as the universe expands. The vacuum remains a sea of subtle activity, a field that never completely rests, even when everything else does. With no significant sources of light, no ongoing fusion, no interactions that can create high-energy photons, the universe rests in a state that cosmologists describe as darkness, but not darkness in the human sense. It is not blackness. It is simply the absence of events that produce or exchange energy. A universe made of extremely rare particles in an expanding void is a universe where structure, energy flow, and illumination have all ended. It is a place where the distinction between matter and radiation has blurred to near irrelevance. The cosmos continues to expand, but expansion no longer changes anything. It simply stretches the already thin fabric of particles across even wider distances. The silence of this era is total, not because sound cannot travel in space, that has always been true, but because the universe itself stops doing things. The passage of time becomes almost indistinguishable from its absence. Without events, without change, without processes unfolding, time loses its functional meaning. It continues as a parameter in physical equations, but the universe no longer provides markers that differentiate one moment from the next. The lightless era is the deepest quiet the cosmos has ever known. It is the final consequence of entropy, expansion, and the steady loss of available energy. After trillions upon trillions of years, after all stars have died and black holes have evaporated, the universe enters this state not with a bang or a collapse, but with a gradual fading into stillness. In this vast, cold silence, the journey of light comes to an end. The universe, once radiant with stars and glowing with the afterglow of creation, becomes a place where light no longer shapes its destiny. And what remains is a cosmos defined almost entirely by absence, an expanding void punctuated only by the rarest particles drifting through infinite darkness. The universe, now thin and silent, reaches a stage where almost nothing familiar remains. No stars, no galaxies, no black holes, only a scattering of particles drifting through a space that feels almost emptied of structure. Yet even here, in a cosmos nearly stripped to its barest form, the deepest questions in physics continue to matter. The late-time universe is shaped not just by what has faded, but by what still persists, the quantum vacuum and the force driving cosmic expansion. In modern physics, the vacuum is never truly empty. It is a field-filled environment where particles flicker in and out of existence, and where the energy of empty space determines the behavior of the entire universe. Whether the vacuum is truly stable or only temporarily stable becomes one of the most important questions in determining the final fate of everything. If the vacuum is metastable, it is like a ball resting in a shallow valley. For now, it is stable enough, but quantum mechanics allows the possibility, however faint, that it could tunnel into a deeper valley, a state of lower energy. This process, called vacuum decay, is not an explosion or collapse in the traditional sense. Instead, a tiny region of space could spontaneously shift into a lower energy state, forming a bubble of true vacuum. This bubble would then expand outward at nearly the speed of light, rewriting the laws of physics wherever it passes. Inside such a bubble, particle masses could change, forces might behave differently, chemistry could become impossible, space-time geometry itself could alter. Everything that existed in the old vacuum would be replaced instantly. There would be no warning, no precursor signal, and no survivors. Not because of destruction, but because the universe inside the bubble would not allow matter, atoms, or anything recognizable to continue existing. The likelihood of this happening depends on the shape of the Higgs potential, the energy landscape that determines how the Higgs field settles into its preferred value. Measurements of the Higgs boson and the top quark place our universe alarmingly close to the metastable region. The vacuum seems safe for now, but the possibility of eventual decay remains open. The timescales predicted are beyond comprehension, vastly longer than the evaporation of even the largest black holes. Vacuum decay is possible, but inconceivably unlikely within any timeline shorter than the farthest future imaginable. While vacuum stability looms as a fundamental question, the other major player in the universe's final destiny is dark energy, the mysterious agent responsible for accelerating cosmic expansion. Observations show that dark energy behaves very much like a constant energy density filling space, similar to Einstein's cosmological constant. But this behavior could change over time, and the universe's future depends entirely on whether dark energy stays constant, grows stronger, or fades away. If dark energy remains constant, the universe continues drifting toward heat death. Expansion accelerates steadily but predictably. Distances increase exponentially. Galaxies recede beyond each other's horizons. Space becomes colder, approaching temperatures so close to absolute zero that the distinction becomes academic. In this scenario, entropy reaches its maximum. The universe becomes a thin, quiet haze of particles spread too far apart to interact. Nothing collapses or explodes. Everything simply fades into a state of uniformity. If dark energy grows stronger with time, if its pressure becomes more negative, the universe takes a radically different path. This scenario involves phantom energy, with properties even stranger than ordinary dark energy. Here, expansion accelerates so violently that it eventually overpowers gravity, electromagnetic forces, and even the strong nuclear force. Structures are torn apart in stages. First, galaxy clusters are disrupted, then galaxies, then star systems, then planets, then molecules, and finally atoms themselves. In the last moments, even space-time becomes unstable and stretches apart. This is the Big Rip, a spectacular but highly speculative end to the cosmos. Current observational data do not favour phantom energy. Measurements of distant supernova, cosmic structure, and the cosmic microwave background all suggest dark energy is consistent with a constant value. But uncertainties in measurement leave small room for exotic behaviours. The Big Rip remains mathematically possible, even if unlikely. The third possibility is that dark energy slowly decays. If its energy density decreases over extremely long timescales, the universe's expansion could slow and eventually halt. If it decays entirely, gravity might regain control. Over vast durations, the expansion could reverse. The universe would begin contracting, not into a hot, explosive collapse like classical models of the Big Crunch, but into a cold, dark implosion. This cold collapse begins quietly. With no stars or radiation left, contraction does not heat the cosmos until the very end. The universe shrinks, temperatures rise from near zero, and in the final moments the contraction accelerates into a high-energy final state. Whether this leads to a bounce, a singularity, or something stranger remains unknown, but current evidence strongly favours a constant dark energy scenario, making this collapse unlikely. These three paths, constant dark energy, phantom energy, or decaying dark energy, define the main cosmological futures consistent with general relativity and quantum field theory. Yet all are subject to uncertainties. Dark energy might couple to other fields. The vacuum could transition to a different state. Quantum gravitational effects could alter extreme futures in ways we cannot yet predict. Observational limits today tell us only what dark energy has done so far, not what it will do in the next trillion years. In the far future universe where almost nothing remains and physical processes slow to near standstill, these deep rules of vacuum structure and cosmic expansion become the final sculptors of destiny, the familiar stages of cosmic evolution, star birth, galaxy formation, nuclear fusion, black hole growth have all ended. What remains are the most fundamental aspects of physics, determining whether the universe drifts toward eternal emptiness, tears itself apart, collapses inward, or undergoes a final quantum transition that rewrites the laws of nature themselves. Even when the cosmos appears nearly lifeless, when the last structures have dissolved and when time seems to have lost most of its meaning, the universe is still governed by these hidden dynamics. Space is never truly empty. The vacuum is a living field. Dark energy continues to shape everything, even in unimaginable silence. And the laws of quantum mechanics wait patiently, capable of altering the universe in a single, unpredictable instant. In the end, the fate of everything is written not in stars or galaxies, but in the deep geometry of space-time and the quiet energy of the vacuum itself. In a universe where structure has unravelled and where change becomes so rare it may as well have stopped, the idea of time itself becomes fragile. Our intuitions about time depend on motion, memory, sequence, and transformation. Heat flowing from hot to cold, stars forming and dying, entropy increasing. But when entropy has reached its maximum and all gradients are exhausted, the universe raises a profound question. If nothing changes, does time still exist? In physics, time is not defined by clocks. Clocks merely measure processes. Time is defined by the evolution of states. If the universe reaches a condition where everything is uniform and static, no particles interacting, no energy moving, no events unfolding, Then the physical markers that give time meaning disappear. Time, in this sense, does not end, but becomes irrelevant. It continues mathematically, but the universe no longer experiences it in any practical or measurable way. It is a dimension without events, the backdrop to a frozen stage. This is not merely a philosophical idea. In thermodynamics, time's arrow emerges from entropy. A heat-death universe has no entropy gradients left to drive the arrow. Without an arrow of time, the distinction between past and future loses substance. Time still exists in the equations, but its direction no longer has physical expression. Some physicists, however, argue that the universe might not remain in a static heat-death state forever. Roger Penrose's conformal cyclic cosmology, CCC, presents a radically different possibility. Penrose proposes that the far future heat-death state, an ultra-dilute universe filled only with radiation and massless particles, may become indistinguishable from the very early universe that preceded the Big Bang. In 330, when all mass decays or evaporates, scale becomes meaningless. Without mass, there is no way to define size, and the geometry of the universe becomes conformally equivalent to a new Big Bang. In this picture, what looks to us like an ending is really the beginning of a new aeon, a fresh universe born from the infinitely stretched end of the previous one. Time does not end. It loops through cycles of expansion, smoothing, and rebirth. Entropy resets, not because it decreases, but because, in the absence of mass, the concept becomes meaningless. Whether CCC describes reality remains unknown, but it offers one of the most imaginative, mathematically elegant bridges between the end of time and the beginning of another. On the opposite end of speculation lies one of the strangest predictions of statistical mechanics: the possibility of Boltzmann brains. In a universe that persists for infinite time, even incredibly improbable events might eventually occur through random fluctuations. One such event could be the spontaneous formation of a self-aware observer, a brain, from random quantum fluctuations in an empty universe. The idea was introduced as a paradox, not a literal prediction. If the universe lasts forever, the argument goes, random brains could vastly outnumber observers who arose through natural evolution, raising questions about why we find ourselves in a structured universe instead of a random one. Most physicists regard Boltzmann brains as evidence that infinite time models may need constraints. If your cosmological model predicts vastly more random observers than evolved ones, the model is probably flawed. Still, the idea highlights a deep tension between time, entropy, and the meaning of observation in extreme futures. Another concept that emerges in discussions of cosmic destiny is quantum recurrence. In certain models, if the universe is finite in energy and volume, then after an insanely long time, 10 to the power of 10 to the power of 10 to the power of years, with exponents stacking beyond comprehension, it might spontaneously return to a configuration extremely close to its initial state. It's a strange idea. Everything that happens could, in theory, happen again by chance alone. Entire galaxies, civilizations, and histories could reappear, not through cycles of expansion and contraction, but through statistical recurrence. However, recurrence requires a finite, closed, non-expanding universe. In an ever-expanding cosmos driven by dark energy, recurrence becomes effectively impossible. Expansion prevents the universe from occupying a fixed energy state. The volume grows without bound. Energy spreads too thin for any meaningful fluctuation to generate a structured region again. Eternal expansion removes the conditions for recurrence, replacing it with an endless drift toward emptiness. In a universe without recurrence and without cycles, the end of time is not a return, but a dissolution into simplicity. This raises a final question. What does observer even mean in a universe without structure? Observation requires interaction. It requires an entity capable of perceiving differences in states. But in a universe where nothing changes and no gradients exist, the concept of observation becomes undefined. There are no physical processes left that can encode memory. There are no systems capable of sustaining complex states. There are no environments where an observer could exist. Observation depends on entropy gradients and the ability to store information, both of which disappear in the heat-death universe. In this sense, time ends when observers do. Not in the literal sense, but in the experiential one. Without observers, without processes, without change, time becomes an uninhabited dimension. It continues only as part of the mathematical fabric of physics, not as a lived or measured reality. The final irony is that the universe does not decide between these speculative endings. It simply evolves according to laws that are already in place. Whether time ends because nothing changes, loops into another cycle, recurs statistically, or abruptly transforms through vacuum decay, depends on parameters we are only beginning to measure and understand. Our present-day universe, full of complexity, structure, and life, represents only a brief window in which time has texture, where events unfold, where memory accumulates, where observers exist. In the deep future, long after all structure has unravelled, the nature of time becomes a question that only physics can answer, but that no observer will remain to witness. The universe's final fate is written not in human experience, but in the thermodynamic and quantum foundations of reality. And whether time ends, resets, loops, or fades into irrelevance, the transition marks not a moment, but the quiet conclusion of change itself. In the face of a universe destined for silence, it's natural to feel small. Yet humans have always tried to imagine the end of everything. Long before astronomy, long before physics, people looked up at the night sky and wondered how long the world would last. Ancient myths described cosmic cycles, awakenings, destructions, and rebirths. The Norse imagined a winter that would swallow the world. Hindu cosmology spoke of universes emerging and dissolving across endless cycles. Greek philosophers speculated about eternal fire and cosmic breath. Even without scientific tools, people sensed that the cosmos might have a story much larger than themselves. Today, science pushes that instinct further. Instead of legends, we use equations, observations, and models to peer across impossible stretches of time. We can trace the evolution of stars, map the expansion of space, and estimate the fates of galaxies. And yet, even with all the mathematics in place, there's a humility in these predictions. The timescales involved, trillions of years, followed by exponentially longer spans, are so vast they almost escape meaning. They stretch beyond the lifetime of any physical structure we know. They stretch beyond language. To imagine the universe in its late stages is not to claim certainty, but to acknowledge the fragility of our moment. Everything we know, the warmth of sunlight, the structure of galaxies, the existence of life, is a local, temporary arrangement of matter and energy. The cosmos has not always looked this way, and it will not always continue to. We live in the luminous chapter between the violent heat of the beginning and the quiet cold of the end. There is something grounding in that perspective. When we picture the final darkness, the thinning of matter, the stretching of space, we are reminded that our entire existence unfolds inside a very specific, very fortunate cosmic window. Stars burn steadily. Heavy elements exist. Planets orbit in stable patterns. Chemistry works. These conditions, so normal to us, are actually fleeting arrangements in a universe that spends most of its time in states far simpler, far quieter, far more uniform than the one we inhabit. Imagining the end of time isn't morbid, though it might seem that way at first. It's a way of seeing clearly. It brings into focus not just the scale of the cosmos, but the preciousness of the present. The everyday things, air, warmth, sunlight, the presence of people around us, belong to a universe that is still rich with structure. A universe where energy still flows and time still has direction. a universe filled with processes, movement and complexity. This perspective encourages a kind of cosmic humility. We may understand some of the rules that shape the far future, but we remain small participants in a much larger story. Our predictions stretch far beyond the lifespan of any species, star, or galaxy, and yet they rest on physical laws that we are still trying to fully understand. There is something beautiful in that uncertainty. It reminds us that science is not just about knowing, it is about exploring, questioning, and imagining possibilities across all scales of time. And when we imagine the universe drifting into stillness, it becomes easier to appreciate how alive it is right now, how full it is. Every star in the night sky is a reminder that fusion still burns. Every galaxy we photograph is a reminder that structure still persists. Every moment of warmth, every movement of light across a room, every breath we take is a quiet sign that the cosmos is still early in its story. As the universe ages, change slows. Eventually it may cease to matter at all, but we exist in the era where change is abundant, where the arrow of time is strong, where the universe is vibrant and complex. Reflecting on its distant fate can make the present feel gentler, more meaningful, more worthy of attention. So as you rest here, with these thoughts drifting softly behind your eyes, let the vastness of time settle into something calm, not frightening, not overwhelming, just quiet. The universe may be immense, and its future may be silent, but right now there is warmth, motion, structure, and life. And in this small, bright moment within a cosmic timeline that almost defies imagination, the simple act of being here is enough. Let the mind loosen, let the world grow softer. The universe has billions upon billions of years ahead of it, but you only have this moment, and it is peaceful.